this is the precise title of my talk. I mean, all that long title reduces to this. It's the construction of a smooth foliation of the dimension 1 in the sphere S5 by complex surfaces. And this is a joint work in collaboration with Laurent Mercier and Universidad. And here's my name. This is my institute, Cuernavaca, where the all-seasonal hypothesis of Jack Milnor for the city of eternal spring, so no winter. So it falls automatically. Maybe not interested for that few points. So let me state a precise theorem. So this is the theorem. So the sphere is 5-dimensional sphere, possesses a smooth codimension 1 integral and limit flat CR structure. That means, for my purpose, that we can foliate, as I told you, the sphere, a smooth foliation, in such a way that each leaf has real dimension 4, so it's the right dimension, and possesses an integral complex structure. So it's created by complex surface, and of course the complex structure varies differentially. This, in terms for people working in complex analysis, I just learned from Mary Hill. It's called a integral Levy-flat CR structure of type 2 million complex leaves of dimension 2, 1 million real one-dimensional transverse direction. So this is the purpose of my talk, presenting you with this example. Let me first point out to you something that we know very well, is that if we have a three-dimensional manifold, which is foliated by surfaces, smooth foliation then by choosing a Riemannian metric, which is automatically, you can choose an almost complex structure in each leaf, and therefore it's automatically integrable. So this problem it's really easy to do. In particular, for instance, the right foliation has such a property, was given the colloquium by Etienne. But just for let me construct the right foliation in an explicit way that example, because it will be useful for my exposition. So let's foliate the sphere S3 in a way that you know, but we'll make it explicit. So we take the complex plane, take the Cartesian product with the real line, so that's R3, and for this subtract the negative vertical axis and 0. So minus 0t, set for 0t, such that t is less or equal to 0. So you subtract this axis, and then consider the diffeomorphism h from, let's call this, let's say x, and let's consider h from x to x, diffeomorphism, which is explicitly given by the following. Well, let's call it t letter. V of set t equals lambda t, h of t, where h, which lambda is a real number strictly greater than 1, and where h is a diffeomorphism from the real line to itself, and the graph looks as follows. The identity for t is strictly negative, and it has the derivative is strictly greater than 1 for t is strictly positive, and then of course h acts properly and discontinuously on x. This x has a natural foliation by complex objects, namely horizontal things. From t0 or negative, the leaves are copies of C star, punctured with the complex plane, and from t strictly positive, it's copies of C. Let's see. No wonder I was okay. So it's if you want, this is called a homothetic transformation, damped homothetic transformation, if you want to give a name. Of course, you take a small ball, you can see that the quotient space will be, the quotient space exists because it acts properly and discontinuously, and what you get is a solid torus which you attach a color, and the color is minus infinity t cross T2. And therefore, the reason for doing that is that the Auxiliary condition is satisfied. So this is foliated as follows. All leaves strictly positive third coordinate are permuted. This leaf passing through zero becomes a elliptic curve, and all the others are elliptic curves. So the foliation, you have the solid torus with a polar, usually polar. Okay, and now I forget about this part because this is only a gluing condition. Okay, and what I get is exactly the red foliation. And this example, the reason I want to tell you this example, which you know very well, is that if you take the action of C star on the upper half plane, closed upper half plane, given by homothetic transformations on the which takes the leaf and are homothetic, commutes with this action. And what this means is the following: is that if you take the solid torus and consider this foliation by Riemann surfaces, any translation in the elliptic curve that is the boundary extends automatically to the interior, because this commute. Then you take your tire of your car, and I better act. So you have the tire of your car is foliated, as you know, by the leaves of Quetzalcoatl with the serpent that eats itself, and then given any isometry, it's just like in the service station. This extends as by holomorphic maps, or you can actually do it. You can actually, or use a wheel. So that's a very simple. So the purpose of my talk is to generalize this simple construction to a more complicated situation. And so let me tell you a little bit of history, because this shows how much the work of Jack Milnor influenced my life, my mathematical life, and many Mexicans, by the way. And so 30 years ago, Larry Lawson, a member of this institute, a person I love very much, discovered in Impa, Brazil, by the way, the first example of a smooth dimension 1 foliation on the series 5. And that is very dear to me because I attended the seminar in which she presented that one. But of course, to achieve this, also using one of the theorems that I love the most. I've always been in love with this theorem. And it's, well, the Milnor vibration theory for isolated complex singularities. In this book, which we all know, it's a jewel of book. And here you have the references. I was very lucky that I worked on this exactly, the name of Milnor appears, so it fits exactly, it's the first time it happens to me. So I'm very happy. Okay. So one property, I will explain you the means what Milnor's vibration theorem is that one property of this loss of foliation that I will immediately describe to you has the property that each leaf individually, separately, is in a natural way a complex surface. And the problem is what I stated, because there exists a smooth dimension 1 foliation, etc. Repeat the same thing. And that is because, you see, this foliation will have compact leaves, and that means that if you give a complex structure to the non-compact leaves, and if they accumulate to the compact leaf, so to speak, the ends, the complex structure of the ends of the leaf are predetermined by the compact leaf. They're trapped by the compact leaf, so there's one difficulty. And therefore, that's what makes the problem difficult. It's the same thing. See, I'm repeating the thing. In other words, if you are given a holomorphic infinity foliation of even dimensional leaves, such a way that they have no complex structure, there's no hope to do anything. This foliation of Lawson has each individual leaf a complex manifest. You might hope to have an actually complex structure, but as I'm telling you, this is obviously non-trivial because complex structure are trapped by the compact leaves. So essentially, it's the same thing. Is the same property of that one. So let me just make precise what I mean by. Just to complete this, what I mean by, So it's exactly what you think. In other words, can one find a smooth foliated atlas, script A, such that we model R5 described as C2 cross R, such that the changes of charts are of this particular type, which we know very well here at the University of Lamination. So, okay. So these are holomorphic in the tangential direction. So here's a small picture to tell you, and that's what it means can we provide. So all these things are CR structure, etc., integrally are equivalent to this statement. Okay. Yeah. Ah, okay, very good. As you can see, I'm not very. Okay, let me see if let's try to. Okay, so this is what I already gave the theory. So let's begin by recalling exactly the Milnor fibration theorem and the way that Lawson achieved this beautiful result. Perhaps I make a parenthesis. When he gave this beautiful proof in Brazil, he sent it to the French people working on foliation. Graves, Reb, Keplier, Rosenberg, Rosary, and 1 week later he received a letter like that saying "Bravo," and signed by all these people. That was very. So let's consider, now we'll explain what the Milnor fibration is. Let's consider a cubic polynomial, a homogeneous polynomial. Is that written there? Okay, and now we consider what is called the singular Milnor fiber. So it's V. And then we have the following schematically picture. So we have C3. This is a homogeneous polynomial. So this object is a complex cone. Okay, and all the other complex numbers different from 0 are regular values. So we have a picture like that, exactly like that. And then from this complex term, we subtract 0. So the only singularity, the singularity is isolated. So we have this picture that I just put here. This is exactly an object and a singular algebraic surface with an isolated singularity, which we will delete like that. And then this W, which is not a manifold, intersects transversely the sphere S5 into a compact manifold, which we call K. It's usually called the link of the isolated singularity. Okay, I wrote this beautifully explained in this book that I love, and I think everybody should read. So beautiful, and you will. And so we have that, and it's called a Briscoe manifold. Okay, and let's see. I'm a little bit dyslexic, so let me hold it like that. Okay, let me see. That. So we have a natural projection, which is simply a projectivization. This is a cubic equation, so projection is a cubic, non-singular, therefore it's an elliptic curve. This elliptic curve has obviously an automorphism of order 3, expressed by cubic root of unity, and therefore, yeah. What? W is the deleted, the puncture Milnor, singular Milnor fiber. So if you take
okay.
we subtract the origin from here, so it's open cone, complex cone, and then obviously this projectivizes to a cubic. In fact, the Fermat cubic has an automorphism of order 3, therefore we know exactly where it sits in moduli space. It's precisely here, cubic root of unity. And this projection is holomorphic, clearly, and describes this W that you say as a principal C-star bundle over this elliptic curve. So it's because you were careful to delete 0. So we have this situation. Here I just mention again that we know exactly which elliptic curve it is. So we have this situation like that. And in fact, therefore, we have the following thing. We have that K, which is the intersection, the link, the intersection of this singularity with the sphere. Therefore, this K also fibers of the elliptic curve EW, and fiber is a circle. Therefore, the only thing we have to know to completely understand that is the Kerr class. And in fact, we go one step further, and we project it to the circle. Then K fibers of the circle with fibers of the torus, and that for us dynamic consistence is better because now it has suspension. And in fact, it's a suspension not of 2, 1, 1, 1, as we are used to, but of 1, minus 3, 0, 1. So it's a unipotent limit, certainly not hyperbolic, doesn't matter. And therefore, you have from this description as a semi-direct product of the integers Z and Z2, you have this explicit presentation of the fundamental group, from which you can compute a particular, for instance, the first cohomology group, and you can compute everything. Okay? So you have a thing. But in fact, yes. Yeah, it's not the sphere. You know, therefore, usually the notation of knot means Sn embedding Sn plus 2. So, but in fact, will be noted in some sense because the Milnor fiber, something I will explain a little later, is 3. It's 3. So, therefore, wait, where am I? Let's see. It's not very complicated, so I put that here. Here. In fact, in yet another beautiful paper by Jack Milnor, I tell you I'm so lucky that I work in this problem because I will be mentioning Milnor all the time. So it's called On the Three-Dimensional Briscoe Manifolds NPQR. It's published by Princeton University Press. The editor is new. I think it's called Links, Praise, and in that pages. So a Briscoe manifold in general, or NPQR, is you do the same thing, except now you change this by P, Q, and R integers. So we're taking 3, 3, 3. I recall you that 1/3 plus 1/3 plus 1/3 is 1. And therefore, this beautiful paper, Milnor characterizes completely these manifolds. He shows that in fact, K can also be described as a mini-manifold. Namely, you take the Heisenberg group, and you divide by those integer matrices, upper triangular, so that alpha, beta, gamma are multiples of 3, and therefore you can explicitly compute the first homology group. Of course, the torus survives, so Z2 plus torsion, E-torsion, that's exactly H1. So it's a very, very beautiful, completely describable object. In this paper, which paper by Milnor, I consider, you know, well, you read Felix-Klein, well, I'm going out of the particular. You read Felix-Klein, the cosahedral, and then what you do, you read Milnor, and that's exactly what I did, and so beautiful. And here comes an explanation of Milnor's celebrated vibration theorem for a particular case that is interesting to us. Namely, if you subtract from this sphere the link A, then it makes sense to speak of F divided by the absolute value of F, because we subtract the zeros of the denominator, and that means that you have a locally trivial vibration, and it describes S5 as an open book with band in K, with fiber diffeomorphic to any regular image of any regular value. I point out that because my polynomial is homogeneous, in fact it holds in many general cases, this equation for 8 different from 0, they are all affine hypersurfaces, and they are absolutely all obeyed by holomorphism, because you can use a homothetic transformation to take one to the other, so they are all by holomorphic, all these manifolds. And when I say open book, in the sense of Ellman-Winkelkemper, means that is it like a fibrous knot, means that K is a codimension two such compacts or manifold. They complement fibers of the circle by Milnor's vibration theorem, and the closure of each leaf is obtained by just adding the K, and then you spin like that, exactly as when you open the door. So you have to cross the wall and come back, and then you have monodromy. So K, the boundary of the hinge, if you like doors better, it's a hinge, and so you use it as a hinge K, you go around, and you come back, and you have a monodromy. Well, on the other hand, K is given by explicit equations, by implicit function theorem, and therefore it has trivial normal bundle, as one can learn from a beautiful book called Topology from the Differential Viewpoint, written by Milnor, as I learned from. So, has trivial normal bundle, and therefore has a tubular neighborhood isomorphic to the link cross the disk. So this is precisely the I'm getting better into this. Okay, that now right here. Yeah. Well, so we arrive to the following conclusion. Both the complement of a cross tubular neighborhood of K and the cross tubular neighborhood itself fiber both of raised ones with vibration, good vibration, such that they are also vibration when you restrict them to the boundary. Then they are smoothly foliated with the boundary as a leaf by two Villon, but in the notation of John Milnor, it's called, I hope I wrote it properly, is correctly ramification, which I will explain in a second. Ramification for this context is exactly doing what I did here to foliate, to obtain the, that's the reason I draw the picture that I already erased. Meaning, if something fibers of the circle, any manifold fibers of the circle, then that corresponds essentially to an infinite cyclic covering as a map to the circle. And then, of course, to know a lot about infinite cyclic coverings, you read John Milnor's paper called Infinite, but that's true, infinite cyclic coverings, and I will give you the reference a little later. And therefore, you unfold the fiber fibers of the circle, means you can unroll the manifold. Think of it as a cylinder. Once you have that, you have the red picture. And you put graphs of the base, graphs of a smooth function of the base, and then that's invariant on the chart. Here I'm cheating because the monodromy is not identity. Okay? And by the way, I forgot to tell you what is the monodromy. In this case, the Milnor vibration theorem is easier because the polynomial is homogeneous. And you can immediately verify that the pages of this vibration F over norm of F are transverse to the top fiber, and therefore you have a flow transverse, a periodic flow transverse to the fibers, and therefore the monodromy is extremely easy to describe, simply the Poincaré map, or first return map. And you can easily see that for this case, it's simply multiplication by the primitive cube probability. Okay? Okay, so this is, therefore, once you have that, a canonical argument array tells you can take both pieces, close tubular neighborhood, complement of the open tubular neighborhood, foliate smoothly, and glue them. Although, to glue two things is you have to be careful because maybe the holonomy of one is the identity of one side and the other is a homothetic transformation. And that's the reason I gave you this example. But as I learned 30 years ago by letter from Sandow, an argument by John Milnor, you can always glue that differential. I guess he knows how to do things because he takes a disk of dimension 6, another disk of dimension 6, and you glue them by the boundary. Well, sometimes you get some absolutely gorgeous, but this is dimension 7, sorry, whose boundary is S6, do the boundaries. So I think Professor Milnor knows how to do it okay, because you can get in fact exotic species, 28 beautiful soil, but this is easier than that. So you can actually do foliations like that. So you have that. So this is the way that Leigh Lawson managed to obtain an incredible example, because one must bear in mind that there were really not examples of foliation. There were suspensions, there were actions, big groups, the right foliation, taking a close curve and removing a tubular mechanism. And really there were no, and of course later came Bill Thorston, and therefore finished the one. Anytime there's a reason for foliation to exist, it exists. So, but anyhow, it was very important for us historically to be solved by Leigh Lawson. Okay. So again, now going back to our problem, maybe I hope I didn't do a mistake and put. No, it's okay. Okay. Now let's do the following. We'll always consider the following situation. We have the elliptic curve, and we know that W, which is the deleted singular Milnor fiber. These fibers is a C-star vibration, and therefore I can take an infinite cyclic covering. So I think of an elliptic curve as a Hopf manifold. Namely, it's obtained by homothetic transformation. The module of the homothetic, I thought it was the logarithm, but that's, you have to multiply C star by that in order to get that elliptic curve, E omega. And you take the pullback. Now C star is Stein. This is a holomorphic C star bundle, and therefore the pullback is a trivial. It's a trivial C star bundle, and therefore here I can put C star cross C star, and if we have this pullback like that. We have this pullback diagram, and I told you the reason we can describe this as a trivial holomorphic product is because Stein is of C star. So we have this diagram like that, and let's see. And then we see immediately paying a cyclic covering that we can recover omega. Yeah, I'm sorry, I say omega is being W. Omega is by holomorphic to the portion of C star cross C star by the action of the form like that. So we're taking this pullback, and therefore to recover that is a homothetic transformation of the first factor, and here is there's a factor of automorphy. The triviality implies that the deck transformation has to be exactly the other way. And this 3 is because I told you the Chern class is -3. And therefore, CW1. Sorry. Where is it? I did it by memory. I know this is not. Okay, W1. So I mean you go from one fiber to the other by a homothetic transformation that depends on the point on the first factor. And that's so sorry. So it's this over here is W omega 1, W1 like that. Sorry, because in my first notation I used W. And wait, now I have to close that. Open that. Okay. Okay, so have now. In fact, it's not so easy to get. I mean, we know that C has to be of that way. The homothetic transformation is not so easy to get, but it's a. I mean, if you read Montfort's, it's actually a quotient of theta function, whose nature we don't care. And now we take lambda for a number greater than 1, we fix all this quotient lambda from now on, and then we consider H from omega to omega given by that. So what we are doing is as if we were doing a Hopf manifold. Here we have W, and then in the same way we get Hopf manifolds, we multiply by homothetic transformation, right? And therefore what we get is a complex surface, compact, and in fact the quotient space, so we're consider omega, and we are taking this homothetic transformation as if it was Hopf manifold, the same construction as Hopf manifold, like that. Okay, and because what we want to do is to obtain a compact surface, and then of course the action is proper, free, uniform, and this W divided by this homothetic transformation gives you a surface. It's obviously diffeomorphic to the link process 1, have fundamental domain with the link cross an interval, right? And in fact, it's a holomorphic principal bundle over the elliptic curve with fiber another elliptic curve. This modulus is still precisely in that formula. And because we know that K, we get an explicit presentation of fundamental group, we can easily see that, well, by QF if you want, the first homology group of K crosses 1 is a complex surface, is lambda being the parameter we use. It's an elliptic fibration in the sense of collider. The fiber is an elliptic curve, which we know, the dot Q, and the fiber is another elliptic curve. But because this first Betti number is off, it's a surface which is not Kähler. Okay, that's it. That's the only remark I want to make. So we have that. Perhaps before I forget to do it, let me do the following. Here we have to keep in mind. So we have the sphere S5. This picture we must always keep in mind. We have the link, which of course I draw as a circle for lack of space. This is of course a Milne manifold of dimension 3. This is the hinge or binding, and then all the pages of this book or the position of the door are, I will mention this are of this type, of the diffeomorphism type of Fi1 of Z, different from 0. And because I remember I give given you the cubic, the Brisker manifold 333, the Milnor number, this singularity is equal to 8. And another theorem by John Milnor says that the non-singular Milnor fiber for this weighted homogeneous case has the homotopy type of a bouquet of two spheres, S2, as many as the Milnor number. So these doors that the revolving door that I'm talking about is actually a very complicated object, and the homotopy type of 8 copies of the sphere S2. So it's a very complicated. And then what we do, the turbularization or reunification, is to, before we come to the hinge, we turbularize. That is best to act with to write the formula, right? And then these K fibers over S1, so we revivify. It's better, but I bet you understand me what I'm saying, no better than that. Okay? And then that's where you have it. That's where we are trying to put a complex structure into. We won't be able to. We have to do a little bit tweak, line modification. We have to actually put a color in the spirit like Milnor explained, but keeping the complex structure. So I probably should have said that before. That's the aim of the. So we have this in here. Okay, now here comes the reference that I promise you. It's a beautiful thing because you know what, and you learn what the Alexander polynomial is. Fantastic. Highly recommended paper by Milnor. So consider this infinite cyclic covering as before, and we have this diagram. So S lambda is the elliptic surface that fibers over the elliptic curve EW, and I take pull back, and now we observe that C star is Stein, and the vibration is by elliptic curves, and this is automatically holomorphically trivial because of this condition. C star is Stein, and this is exact. These are the...
Alberto, is S lambda boundary of 2, okay?
That's precisely the boundary of the tubular neighborhood of K will be exactly S lambda, because it's K crosses 1 for a very simple reason, right? I told you it was locally trivial. Had trivial normal bundle. No, you're getting to the point exactly. So at least we know the boundary of the tubular neighborhood is this surface, which is K cross S1. So you say, well, and all the other leaves are the Milnor fiber, but then how do you roll? You have to roll, keeping in mind that the complex structure is strata incompatible, so you cannot. Fortunately, perhaps I should, well, I come to that a little later, because otherwise I'm going to get out of the. So, by the standard argument that anybody in algebraic geometry knows, because I'm not an algebraic geometrist, but it's a fact, this vibration is trivial. Then, okay. Okay, no, wait, see, what is this? Page, which page I am? No, it's okay. 15, 17, yes. Sorry, this is the most difficult part. So, let from now on B is a solid torus. It's one across the disk. Well, we know that K fibers of the elliptic curve just compose the first projection into this factor followed by the projection, and then take the same cyclic covering and pull back. So we obtain a manifold X that is C star cross B2. And what now you have to think about it is that, so you have C star, and what you have is actually a solid torus bundle over C star, just like pull back. So, for each point of the puncture plane, you have a tire with an error. Okay, so you have C star. Now to connect it with tennis, the idea you have C star, and this vibration by capital P describes this as a solid torus bundle. Okay. Now what I want to do, and of course to recover K cross D2, what do? Well, I take the deck transformation that takes me from X to that, okay? And the deck transformation is what? It's homothetic transformation of the first factor, rotation on the elliptic curve. And now I told you that once you have a tire with the red foliation inside, any isometry of the boundary extends as isometry is over here. And therefore, I expect that this action, well, this has a natural foliation for dimension 1 with the boundary as a leaf. If the obvious one is put the red foliation in the solid torus, right? And be sure that when you take the deck transformations, things are complex structure is preserved, and then what you have is precisely what Dennis was saying. You have a tubular neighborhood foliated. The boundary will be a leaf. The boundary will be, in fact, as Dennis said, S lambda. And now the leaves will be C bundles, holomorphic C bundles over C star. And then, well, divided by an action. And so we have this picture. Think of this as a bunch of tires. The only thing I want you to remember is that the deck transformation is move rotate. No? the monodromy is dictated by, because remember that K fibers over a torus with fiber S1, that is vibration in the trivial has a Chen class minus 3. But it doesn't matter, so we have this situation here. So this is a tire bundle over function plane. Okay, this is speaker. You say tire, no? You say with Y or with I? No, it doesn't matter. No. With Y, you Adam, you are not British. Okay. No, okay, let's call the action of this group, cyclic group that acts, that's what it's an infinite cyclic group, let's call it A. So this action leads to an action of C star. We move this and then what we're going to do is the following idea. I want you to think of this solid torus.
Alberto, understand why this action on C star preserves the homomorphic structure for the S3. But what is the map on C star?
Well, I'm telling you,
you're putting on the complex structure on each.
suppose you only put a complex structure on the boundary. You don't have air on your tires, okay? But the construction I did before said that any translation on the boundary extends canonically in the interior in such a way that the complex structure of the leaves is preserved in a unique way. I give you explicitly. I want to give you explicitly the infinite cyclic coverage. I give you a formula. The formula exists, okay, and preserves the leaves. So let me do it. Let me do it in another way, okay? That will explain completely. Will answer your question. So instead of thinking of the solid torus, you unroll this, and it's the picture that I already erased 3 times. What time is it? And then I take. Remember, I started by saying the following: C star cross R plus. Okay. And then I divided this by a homotelic transformation. And so in my head, I'm going to unroll this and think of this situation. That's the best way to get red foliation, right? And in my head, I unroll that one, and that's the way I will get an explicit formula that will tell you that it extends explicitly. Okay, so, and here it is. So let X tilde be C star cross the upper half plane, the upper half space, described as Z cross R, with the 0 deleted, right? Exactly like that. And then consider this action here. This, the action of Z2, Z plus Z, given by generators T and S, which obviously we can use. Okay? Now observe that X tilde has a natural foliation. I think to the form C star cross with the obvious foliation. Every time you see C or C star, you fix T. And this action obviously preserves your steam, and that answers your question. You roll, not only answer your question, but actually you were able to foliate a tubular neighborhood in such a way that the gluing condition is, because you have to be careful when you glue, as I told you, in such a way that the gluing condition is satisfied. The gluing condition means you can extend actually the foliation in a trivial way by adding a color together with the CR legislator complex structure. And then the gluing condition is satisfied. And therefore I have one piece already foliated by complex surfaces. Okay. Now my objective is to actually foliate the complex. So I have one piece of the puzzle. I put it here, ready to glue. Okay. And now my objective is to actually glue the other part. Okay. Now, here's, it's written exactly what I said. This half space, deleted half space bundle over C star has a natural foliation, here described. Only one exotic leaf, which is C star cross 0, has these two halves. The action by the group generated by S and T is released by holomorphically to leaves, acts proper discontinuously beautifully, and therefore that means that K cross D2, which is the cross tubular neighborhood of the leaf, has a foliation by holomorphic surfaces, and the boundary is the leaf, the given condition is satisfied, and the boundary is a non-Kähler elliptic surface, like Odaira, I think it's Odaira second, I don't remember the Odaira first, something, I don't remember the name, but so you have very nice structure on the leaves, you can tell you how it is. And now my aim is to actually take the revolving door, roll it, you know, tubularize, but in a complex way. So that's the objective. So let's try to do that. Okay, now we have a beautiful so objective. This is the tubular, the interior of the tubular end is the tubular open tubular neighborhood. So we want to foliate the complement of that. Okay, now. I think I'm missing one ingredient here in my notes. I think I say this I explained the black one. Let me explain you something which is very important for my talk. So let's we have to use another. Unfortunately, we have to use another result by Milnor. Unfortunately, yet one more. Maybe probably more. Okay, so remember we have a cubic polynomial. I should have erased this one. So the Fermat polynomial of the cubic person. And I told you that the complement of the lead fibers as is a non-moving composition. Now, for this homogeneous case, in more general cases, but for this homogeneous case in particular, Milnor proved the following beautiful construction. So, you say, what happens if I take f minus 1 of a unit circle? So, this map has an isolated singularity at 0, so you remove the singular fiber, whole, not just the origin, the whole singular fiber, the complement fibers of the C star as a locally trivial vibration. And you can think of the following, you can take the inverse image of the circle, and because this is a, well, actually, I take f restricted to Tc minus d from now on. And that means that if you take the inverse image of the circle, you have a manifold that by its own nature fibers over the circle, and the fibers are the affine surfaces G1 cubed plus C2 cubed plus C2 cubed equals to e to the I theta. They are all by holomorphic. And when you give a full turn, now we understand clearly that the monodromy is multiplication by a root of unity. So this is a mapping torus. Okay, first observation. Second observation is that, so let's draw a picture that will, so think of this way. Okay, so this is the singular fiber, dimension 1 in this picture. All the fibers are round. So these are all the fibers that correspond to this equal to e to the I theta. Okay, and observe that if you take a sphere of enormous radius, each of these leaves will cut. What remains outside is a color, no singularities. Okay, it's a color. And now Milnor proves the following thing: if you cut with this large sphere, and then you blow that so that it becomes tangent to the sphere, you get the Milnor vibration, except when you take a tubular neighborhood of the hinge. In other words, more precise mathematically, if you take the gradient of this, is one of the ways in this beautiful book, is if you take the complex gradient and damp it to become 0 here, this is perpendicular to this surface, and you move by this vector field until you make it tangent to this field, and that is one way to describe Milnor vibration. Beautiful. Another beautiful, like, so that's the way. And I like this way because you see now, you can immediately see that this vibration gives you a manifold fibers of the circle with fibers is affine surface or are by holomorphic, and with the monodromy exactly as another description of the complement of the leaf. Now what I want to do is to use another cyclic cover, infinite cyclic cover, unroll that, and actually it would be better to think in, for instance, the following. Emphasize this equality. Okay, but think of that object. Okay, so you have here the complex plane. Here you have C3, and I'm taking the inverse image of this close, have the positive real line in C. So if I remove the 0, everything is beautiful. If I come to 0, singular fiber, W, but now I remove the origin, C3. Okay, so think of a, let me draw the best way to do it is singular fiber for t equals 0, smooth complex manifold for t positive. Of course, I remind you that these are a cone, and these are manifolds of very complicated. Okay, I almost finished. Have that. And then what happens if I multiply all points here by a homothetic transformation, following homothetic transformation, C1, C2, C3, equals lambda omega C1, lambda omega C2, lambda omega C3. Well, this cone is fixed. What I get when I take the quotient is S lambda, and what I get here is always a Hopf manifold, Hopf-like manifold. The quotient is a compact manifold with boundary. The boundary is precisely S lambda, and this is the way, canonical way to roll. However, it doesn't work exactly that way, because to this object I cannot put a color. I have to modify this slightly by adding by doing a trick, as usual in mathematics. And so you consider a better way to think is a C3 cross R. For T negative, put the cone. For T positive, is smooth Milnor fiber. And then, exactly as I described at the very beginning, the red foliation, you did a transformation in such a way that is the identity. No, it's a homothetic transformation for T negative, and acts like this on the positive, and that way you roll. You can do it everything is infinity. You present the complex structure. You probably here is the explicit construction of the homothetic transformation. So I'm completely mimicking what I did at the very beginning. This simple way to fill your time with a red foliation in such a way that it's invariant. And this way, finally, take first piece and the second piece, glue them together, and I gave you a foliation by complex surface of this side. With that, I'm thanking John Milnor, as I think I used a little bit of the work, but you need to prove that, and happy birthday. No.
transfer
In fact, by Hefliger, already you forget about complex, by Hefliger you cannot, and also by its very nature, the holomorph is identity one side, and exactly, you need to damp the thing. Okay, and so this is the construction of foliation. Hefliger says that on a interconnected manifold, a compact manifold, you cannot have a real analytic foliation, because when you have holonomy that is tangent to is identity in one interval. So now, these people in were born. That's the reason I know it. It's about maybe.
But this foliation is not scalar.
Non-scalar. Ah. No. I tried. No, good question. I couldn't get it. Not with this method, and also another example. I don't think with this one. But I think that things like links, etc., will never be scalar. But that's only an intuitive thing. That would be that's a good question. I don't know the answer, but I think maybe because these are like Kodaira Thorsten examples, and everything is symplectic. You're absolutely correct. I think this is symplectic, but I mean I don't claim that I believe it's actually symplectic. I completely believe that. And also, as you notice, I use a parameter lambda, which I can move freely. Therefore, this foliation has non-trivial deformations in the Kodaira space. In other words, H1 in fancy language that I don't know, H1 of the manifold with coefficients in the tangent sheet, tangent to foliation is not zero, something like that. Something like that. I could write a beautiful formula, but I don't know what. That's what it means. You can't deform perfectly with the complex structure.
But I think this format called is not something.
No. Having all. You mean maybe the second cohomology doesn't go up to the top. No. So for yeah.
Because your example is not reflected because it has compact so
QED, as usual with the QED. But also by the reason that one. The reason I thought is because it sounded like a La Thorsten. I know the example Thorsten Kodaira. But I forgot which one it is. Yeah. But I think it's important. Yeah, I think it's not possible. But it's a very good question, by the way.
How can we learn just using a two-dimensional blackboard and two hands to make such nice six-dimensional pictures?
Well, Adam, I was acting with another colleague in a musical, Irma La Dulce. And I told Professor Jose Adam, hey, Professor, I'm working in this and actually as a comic. And he told me, finally you found your right profession. And I went like, I was so happy. And maybe he's right. Imagine Broadway.